So how can we quantify the degree of conscious seeing? That's the next topic. Um, there are lots of ways to go better than standard kind of numbers such as a percentage of a correct. And one way to go better than that is called signal detection analysis using yes/no response with the visibility or confidence ratings. So visual visibility ratings can disambiguate the level of clarity. Like in the case of backward masking, I can say that I never saw that the target letter very clearly, except for the last SOA. And another one is a confidence rating. Confidence and the visibility rating tend to be very related, but you can potentially also separate the confidence in the decision or visibility in terms of clarity. But anyway, the key here is to analyze the data, behavioral data reports, using a signal detection theory. So what is that? And important point is to that signal detection theory helps you to disambiguate the issue of a subjective criterion. In signal detection theory, we categorize the trials in 4 ways. First, we categorize the trials into stimulus present or stimulus absent. So that's trial categorization. And then another way to categorize a trial is that the response of I saw it. So it's like yes response versus no response. I didn't see it. And then separately, we define each of the entry. So if there was a stimulus and if you agree that there was a stimulus, then we call it as hit. And if there was a stimulus but you deny it, that's called a miss. Similarly, when there was no stimulus and then you agree that no, there was no stimulus, then it's called a correct rejection. And if you detect non-present stimulus, it's called a false alarm. Okay. Now, the model to consider this 4-way response is the following. So you consider 2 distribution of the Gaussian, and both of them is a sample from many trials. Okay, and then for example, let's say when there is a stimulus, then it generates some kind of internal response here, such as a brain response. This is a model, okay? So this is a hypothetical thing. And so in some trials, yes, there was a huge response here and here, sometimes the lower and so on. And then if you collect enough number of trials, then it starts to accumulate into Gaussian like this. On the other hand, if you just look at the brain response in the trial where stimulus is not present, absent, then you tend to see something like lower response like this. But sometimes I see large response, and then if you accumulate many trials, then it ends up in some kind of Gaussian distribution like this. But the problem here is that we as an observer of this response, we don't know whether the response is coming from stimulus present trial or stimulus absent trial. We just have an access to this observed magnitude. So if you just observe the magnitude here, then what you say, is it a present or absent? That's unclear, right? And then signal detection analysis basically assumes that's probably happening in the brain. And then what it says is that, okay, so this is happening in the brain, and what we are going to do in terms of decision making is that we set some kind of a criterion, response criterion, such as here. Okay. And then the trials that exceed this criterion, you'll say yes. And then if it's below, then no. That's the assumption of this model. If you do that, then for the stimulus present trials, the ones that to the right is called hit, right? This part. And then the one that is left to the criterion is miss. And then same goes for the stimulus absent trials. Stimulus absent and still, right side of this, criterion is going to be false alarm, and then left side is going to be correct rejection. So the assumption here is that our response is distributed like Gaussian, and then we are setting some kind of criterion to say yes or no. And then under this assumption, what we can gain is the following. So if there is a subject who is very, very liberal and saying yes all the time, and that corresponds to this, low level, criterion. This particular subject tends to say yes all the time because his, criterion to say yes is very, very low. And there are some subjects, and then in that kind of case, then this subject ends up in, getting most of the stimulus present trial correct, hits, but most of the present stimulus absent trials are wrong, false alarm, lots of them. Now, if there's another subject who sets the criterion a little bit higher, then he loses a bit of the hits, but reduces the false alarm quite a bit. And then if he also raises further criterion, then hits can be 50%, but the false alarm can reduce. And in this case, if you are just counting the number of the correct response, then you might mislead it by like 97% or 84% or 50%. We also need to think about correct rejection, but roughly speaking, this is the kind of the problem of the criterion. Instead, if you use this receiver operating characteristic introduced from signal detection theory, then we can reduce this kind of confusion. So what it means is that when you have this particular criterion that corresponds to hits 97%, so this y-axis is a hits, and then x-axis is a false alarm, 84%, like this, and then you draw one dot, okay, and then you go another try another one by looking at this 84% and false alarm 50%. So that corresponds roughly like hits are hits are 84 and false alarm are 50, and then finally hits are 50% and false alarm are 16%. And if you can do this gradually across different levels of criterion, then you can draw this nice curve, right? And this curve is independent of the criterion, and it just captures the separation of this Gaussian and also degree of the variance of the Gaussian. And this distance between this Gaussian center is called D prime. And you might have heard or seen some papers talking about the D prime, but that's what it is. Separation of the Gaussian. And D prime 1 corresponds roughly like this, D prime 2, D prime 3, D prime 4, that as you see it here. So okay, so then when you use a completely different situation where stimulus is highly visible, and then it's easy to say yes or no, like D prime of 3. Then no matter what kind of criterion you use, you end up in somewhere around here, and then that's a D prime 3 situation. And here hits are very, very high compared to false alarm. Okay. So in practice, how can we estimate receiver operating characteristic by which requires different level of the criterion? this involves a little bit of the explanation about how this actually works. But different criteria can be induced by different level of reward or instruction or probability of stimulus present versus absent. Also, if you ask people to rate the confidence of visibility, then from that we can also estimate a different kind of inflection point for the ROC curve. And if you are interested in how it works or you want to use it for your project, these kind of links are probably useful to go. So in sum, signal detection theory is a powerful and widely used method to objectively quantify the degree of conscious seeing as discriminability. And interestingly, it's less affected by our response criteria. And using this, can we really characterize conscious seeing with the signal detection theory? That's the question. But unfortunately, we are going to take a look at the unconscious detection and also quality of seeing. How do we actually, capture different kinds of seeing? Like, let's say, seeing of the red versus green. It's not possible to just, measure by the D prime, because after some difference, stimulus difference, it becomes always totally visible, change, quantify different kind of, seeing. For example, here, you see a different, my background, Zoom background has many different kind of colors, but presumably you should be able to distinguish between this different range of the orange and so purple and then pink and also blue, right? And each of them are just different, but how different is not possible to characterize by the single number of D prime. So what do we do? So that's a question. And these kind of issues needs to be dealt with, and more to come in the next weeks of the lectures. Okay.